Hello and welcome back. We'll start chapter 7 in this video. So section 7.1 is going to be on confidence intervals and trying to estimate population proportions. So we'll often use samples to estimate population proportions, say like the proportion of a population that will vote in some way or has participated in some activity or something like this. So we're just looking to find a proportion or percentage of a population that satisfies some criterion. And essentially the thing that we'll do the most is we'll use the single value, that is, say, the sample proportion, to estimate the population parameter. And this is just called a point estimate, as in I'll just give you a single value that we expect the population parameter to be. Sample proportions are very good point estimates for population proportions because they are unbiased estimators, meaning that the sample proportions on average, if you were to take a bunch of sample proportions and take their mean, you would expect to get the population proportion. We use p hat to indicate the proportion in a sample. So if you were to go out and ask 100 people if they played sports in high school, this would be a sample proportion. But if you were to go to the entire population and ask if they played sports in high school, we would represent that proportion with just a p. So p hat is just for a sample and p is for the entire population. Now, we can also, rather than just using a single number to try to guess or give a best estimate for a population parameter, we can give an entire range of values. So rather than saying our best guess for the population proportion is 68%, we could say, oh, it's somewhere between these values. So if you give a range, we can be a little bit more confident in our answer. And this is what a confidence interval is. So a confidence interval is going to be a range of values rather than just one value. It's going to be a range of values that we'll use to estimate a parameter. And we can also talk about the confidence level. So if you want to be more confident in your answer, you give a bigger range. So if I said, oh, a parameter for the population is going to be between 65 and 70, I could be more confident if I said the population, the parameter is going to be between 50 and 100. If I have a bigger range, I could be more confident that the interval will actually contain the parameter. If I give a small range, I can't be as confident, but I can be more precise. Here's an example. Let's say that we go out and we take a sample of people and we ask if they played sports in high school, and we find that 20% of people say that they played sports in high school. So for our sample, we would have p hat is 0.2, meaning 20% of people in our sample played sports. So if you were to just ask, what would you expect the entire population, what percentage of the population would you expect to have played sports? Well, we collected a sample for a reason. We would guess that maybe it's 0.2. However, maybe we can't say it's equal to 0.2 exactly because we simply don't know. So maybe we want to give a range of values. So for instance, we could give a confidence interval that could look like this. And we could say our 95% confidence interval is that the actual population, the actual proportion of the population is between 0.17 and 0.23, meaning between 17% and 23% of people played sports. We could be a little bit more confident in our answer here because there's a little bit of wiggle room. There's an extra margin of error that we could be off by, but our actual population parameter could be somewhere in that range. There is a correct way to interpret the statement as well. So we are 95% confident that the actual proportion of people who played sports in high school is between these two numbers. I want to compare this to a couple other seemingly natural ways of phrasing this that are actually incorrect. So there's two incorrect ways that the book touches on in here. So it's incorrect to say there's a 95% chance that P falls between 0.17 and 0.23. P here is not something that is going to change. This isn't a variable. It's not going to fall in here 95% of the time and outside of it 5% of the time. P is a number. It's a fixed number. There is an actual percentage of people that played sports in high school. We can't change that. It's not going to fall in here 95% of the time and it's going to fall outside of it 5% of the time. It is just a number, and it's not going to be changing at all. So this implies that P is changing, which is incorrect. Another incorrect thing to say here is 95% of sample proportions will fall between 0.17 and 0.23. We collected one sample, and that sample we collected had 0.2, as in 20% of people in the sample play sports in high school. We can't make sweeping statements about other samples that we collect. Our one sample might indicate that, sure, if we expect this to be an accurate sample, maybe a lot of samples should be close to it, but our statement about our confidence interval has nothing to do with other samples. So our confidence interval, the correct way to phrase this, is that we are 95% confident that the actual population, the actual parameter, falls within this range. And it's the 95% expresses our confidence in our answer, not about things having to do with P or other sample proportions. So let's draw a little bit of a picture to sort of demonstrate exactly what's going on here. So our confidence level, 1 minus alpha, 1 minus alpha is just a funny way of writing, say 0.95. We would just write it as 1 minus 0.05 instead. So the reason that we're doing this is because if we were to be 100% confident, that would be 100%, that would be 1. But it's hard to be 100% confident in anything, especially if we're only looking at samples. So we allow ourselves a little extra wiggle room, which is this 5% here. So when we're looking at this 95%, sample proportions are going to be normally distributed, meaning if we go out and we take a bunch of samples, the proportions that we'll calculate are going to be normally distributed. And this percent is going to be describing a range of values. So this is going to be 1 minus alpha in here. So maybe 0.95. So this is essentially assuming that if our sample is accurate, we want to be confident that the population parameter is somewhere in this range. And there's a little bit of a tail where the actual population parameter could be, but we're confident that we're in here. So what's left over? If 1 minus alpha is in here, alpha should be the rest of this area. Half of it is going to be over here, and half of it is going to be over here. So if 1 minus alpha is the area in the middle, then alpha divided by 2 should be the area over here, and alpha divided by 2 should be the area over here. And we'll have two z-scores. We're going to have this z-score, and because everything is symmetric, we're going to have the negative of that z-score as well. and these are called the critical values. So we'll just focus on z for the moment, and we'll know that negative z is just going to be on the opposite side. So let's find z and negative z for a particular confidence interval. Let's look at 0.95. So let's find the z-scores associated to a 95% confidence interval. So again, if I draw my my picture, we've got our bell curve, our standard normal distribution, and we want this area in the middle to be 0.95. That means that the area outside of this is going to be 0.5, and furthermore, half of it is going to be on this side, half of it is going to be on this side. So we'll have half of 0.05 is 0.025, and 0.025. So I want to find this z-score here, and this z-score, which is going to be the same as this one. And the trick is, normally with a z-score, we're looking at the area, let's say, to the left or right of this. So let's look at the area to the left of this first. How much of the area is to the left of this? It will be 0.975. 0.95 from here to here, and an extra 0.025 from there. So let's go to our StatCrunch, and we can look at, under statistics, we can go to calculators, look at the normal distribution, and so I want to find the area to the left of the number. That gives me the area of 0.975. So that's going to be 1.9 if we round 6. So 1.96. So if we come back over here, z should equal 1.96. The other way of calculating this, the area to the right, should be 0.025. So let's see if we get the same thing. If I switch and I'm looking at greater than, this area is going to be 0.025. And we have the same z-score. So everything looks correct. Negative z on this side is just going to be negative 1.96. So this z-score would be used to calculate the range of values in our confidence interval. And there's just a couple other critical values here. So if you want a 90% confidence interval, we're allowing ourselves to be less confident. We have a smaller z-score, meaning we'll have a smaller range. So we can be more precise, but less confident in our answer. If we increase our confidence interval, confidence level to 99%, our z-score gets big. So if we want to be more confident in our answer, we're just going to have to give a bigger range of values, which will be being less precise, but more confident. In the next video, I'll talk about how to actually construct the confidence interval and not just the z-scores associated to it.